Hello, Algebra 2 students. This is Mr. Kraft coming to you via the wonders of technology. Today, I'm going to talk about radical expressions, the topics we've talked about the last few days. It will be a longer video than usual because there's a lot of stuff I have to cover. As you may notice, I've put on a little bit of classical study music in the background that will perhaps put you into a soothing frame of mind if the math doesn't soothe you enough already. Okay. So we've been talking about radicals, and a radical is just a root, such as the square root of 9, which is 3. You can have other roots as well, such as the cube root of 8, which is 2. And of course, a root is just the exact opposite of a power. 3 squared is 9, so the square root of 9 is 3. 2 cubed is 8, so the cube root of 8 is 2. Say the fourth root of 81 is 3, because 3 square, 3 to the fourth, 3 times 3 times 3 times 3 is 81. The number that is in the little dip there is called the index. And you all should still have copies of the power table that I gave you that gives squares, cubes, fourths, and I think it also gives fifths. It is available on my blog if you don't have a physical copy of it. And later on, after I get this video done, I'm going to download it and put it up on the Google Classroom site as well. So you'll have various options for getting to it. So this is basically your notation, your indices, your indexes, and your powers. Okay. Now, one thing that is an important rule, suppose I had the square root of, let me think of a good example. The square root of 4 squared. When you have an exponent underneath a radical, that can be rewritten as the radical to that power outside. These two expressions are the same. So 4 squared is 16, and the square root of 16, of course, is 4. But if you did it this way, you would have the square root of 4 is 2, and then 2 squared, which is also 4. Now, with a very simple example such as this, it's not really necessary to be able to do something like that. But if you had something outrageous, like perhaps the square root of 9 to the 5th. 9 to the 5th would be a very large number. It would be 9 times 9 times 9 times 9 times 9, which would be 81 times 81 times 9, 81 times 81, 6,561, then times 9. You see where this is going. It's not fun. 59,049. And trust me, people, you don't want to do that. Not fun. Although with a calculator it wouldn't be that bad, but still. But if you just do this and rewrite that as the square root of 9 quantity to the 5th, Then you have 3 to the 5th. That's not too hard to do. 3 to the 4th is 81. I know that from memory. So the 5th, you just multiply by 9 one more time. 729, which would also be the square root of 59,049. But it's so much easier if you do it this way. And you would avoid even having to use the calculator if you didn't want to do that. Okay, so what I want to talk about now is fractional exponents. Now the logic is this. If you said 9 to the 1/2, what does that possibly mean? Well, it's hard to say. We don't, we've talked about 0 as an exponent. 9 to the 0 is 1, and I've explained why that is. Negative exponents mean a fraction. A fractional exponent just means a root, where the numerator is the exponent and the denominator is the base, except we don't normally write the base of 2 with square roots, so I remove that. And that, of course, is 3. The logic of how you could do this is 9 to the 1/2. This is how you would demonstrate that this works. 9 to the 1/2 times 9 to the 1/2 equals what? Well, the rule is you just add exponents. Just like if I had 9 to the 3rd times 9 to the 4th, that would be 9 to the 7th. Okay, well, a half plus a half is 1, and 9 to the 1st is just 9. Well, if 9 to the half times itself equals 9, then it must be 3, because the number times itself that gives you 9 is 3. Since that's the case, that implies that this must mean a square root. Simple as that. So if you had 8 to the 1/3 power, that would be a cube root. And if you had 8 to the 2/3 power, what do you do then? You have your radical. The denominator is your index. The way I tell students to remember this, denominator is on the bottom, and this is kind of like a drain. It's just swirling around down to the bottom. So the bottom is always your index. The thing on top, well, an exponent is on the top, isn't it? So that's easily enough done. So that would just be the cube root of 64, except by the method I showed you earlier, it would be much easier just to say the cube root of 8 quantity squared. Cube root of 8 is 2, 2 squared is 4. And 4, in fact, is the cube root of 64. Why do we want to use these fractional exponents in general? What's the purpose of them? They actually do, believe it or not, make life easier in some circumstances. Suppose I wanted to say the 3rd root of 8 squared times the 5th root of 8 cubed. What a monstrosity that is. Obviously, you could do it by taking the cube root of the appropriate thing, the 5th root, and all that stuff, work it out manually. That would not be fun. But let's do this. Let's rewrite this in terms of fractional exponents. The exponent inside is at the top, so it goes to the top. Same here. Your index goes to the bottom. Well, now what do? 8 to the 2/3 times 8 to the 3/5. You add exponents. which is 2/3 plus 3/5. And guess what? All the stuff with fractions and common denominators that you hated and probably thought, I'm in Algebra 2 now, I'm doing complicated stuff, I'll never have to do that again. Psych, you have to do it again. But it's not hard. The LCD for 3 and 5 is 15. So 3 times 5 is 15, so you multiply the numerator by the same thing. 5 times 3, 3 times 3, 19 fifteenths. So that would be 8 to the 19 fifteenths, which would be the 15th root of 8 to the 19th. Now, this is really an outrageous example. You can let a breath of relief out because I would never give you something like this to compute, to calculate on a test. That would be ridiculous. But in principle, you have two things that are different roots and you couldn't seem to put them together. If you translate it to fractions, it's easily enough done. And actually, I can tell you what that would be very, very, very close to. It would be a little bit bigger than 8. Now, I'm not a computation machine, but 19 fifteenths is very close to 1. Very, very close to 1. Let's see exactly what it is. $19 divided by 15, 1.3 approximately. So it is about 1.3. Well, 1.3 is 1 3/10 equals 13/10. That's pretty close to what it is. 1.3, 8 to the 1, of course, is going to be 8. 8 squared is 64. This is 8 to the 1.3. So it would be even closer to 1 there. It would be a little bit bigger than 8. But the actual computation, you'd have to do that with the calculator or by other methods. My main point is that it does make working these things easier. Let's look in your textbook on page 295. And let's look at a couple of problems. It says evaluate without using a calculator. So 24, 9 to the 1.5. 25, 32 to the 1.4. And then look at 30, which looks horrible. 1 over 8 to the power of negative 4/3. Okay. 1.5 is 1.5, or as a fraction, 3/2, which means the square root of 9 cubed. Like we said earlier, in a case like that, you can take the cube outside. So you've got the square root of 9, which is 3, cubed, and that is 27. 3 times 3 times 3. Easy. 32 to the 1.4 power. Well, 1.4 equals 1 4/10, which would be 14/10, which would be 7/5. Let me see. Yeah. So you've got 32 to the 7/5 power, which means the 5th root of 32 to the 7th, or the 5th root of 32 to the 7th power. Well, 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32. So 2 to the 5th is 32. So it's not too hard to figure out what the 5th root of 32 is. It's just 2. So 2 to the 7th, well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 more is 64. 1, 2, 3, 4, 5, 6 times 2. So 64 times 2 is 128, which is the answer to that. So that looked awful, but it's not that bad. Let me clear the board and rewrite that so I'll have room for it. So number 30, 1 over 8 to the negative 4/3. Let me make sure I copied that correctly. Yes. So when you have something, this is a totally different example. If you have something to a power, it's a fraction to a power, the exponent goes with both. It distributes. So what happens here is I get 1 to the negative 4/3 over 8 to the negative 4/3. Negative powers mean a fraction, or better, a reciprocal. So it flips. 8 to the 4/3 over 1 to the 4/3. The bottom is easy. 1 to any power is always 1. Easy peasy. And in fact, since it's over 1, that means it's a whole number. I don't even need to write it as a fraction anymore. There's no point to do that. So basically what I've got is 8 to the 4/3 now. Well, that's easy enough. I rewrite it as a root, the cube root of 8 to the 4th, which is the cube root of 8, the whole thing to the 4th. Cube root of 8 is 2. 2 to the 4th is just 16. So I hope I've shown you how these are not as intimidating as they look. This is basically a discussion of what is in chapter 7.2. Now, let's look at 7.3, which is a matter of sums of exponents, or not sums of exponents, sums of radicals. And once again, it's not as bad as it looks. If you have something like this, the square root of 2 plus the square root of 3, that's pretty much the same way as saying x plus y. You can't add x and y. Why? They're unlike terms. Remember way back in algebra, or maybe even pre-algebra, where we talk about getting like terms together. You know, I'm sure with you guys I've talked about SAM, which is how you solve an algebraic equation. Simplify, add, which includes subtraction, and multiply, which includes division. The simplify part's kind of what I'm interested in here. If you had 3x plus 5 minus 2x plus 7, the x's are like terms. 3x minus 2x is 1x, just x. 5 and 7 are like terms. You get 12. You can't go farther than that. Cannot add apples and oranges. This is always where algebra teachers talk about fruit. You know what? Radicals in this context behave just like variables. Square root of 2 is as if it were an x. That's as if it were a y. Apples, oranges, forget about it. You don't do anything more. Okay. Well, if I have apples and apples, though, then we put them together. Likewise, if I had the square root of 2 plus 2 root 2, then we've got, I'm sorry, got carried away and wrote that wrong. No problem. The square root of 2 plus 2 root of 2 gives 3 root of 2. This is understood to be a 1. Okay. We've talked somewhat already about simplifying roots, and this is basically what you do with these kind of things. So let's look on page 298. Whoops.